Hey everybody, this is Miss Smith. So this is day 3 of Forces Vocabulary. So today we're going to talk about Newton's third law of motion. We'll talk about momentum, law of conservation of momentum. We'll talk about types of collisions. So this particular lesson today is going to have a lot of super important information for your egg drop. So make sure that you pay attention closely. So anyway, go ahead and get your notes out, and so you can have this video on in the background. Remember that sometimes I'm going to show you stuff that maybe you would need to see, or I'm going to pull up a YouTube video. So anyway, just be aware and watch out and take good notes. Every time. Free fall. Free fall is when an object is influenced only by the force of gravity. All right, now I'm going to leave a little space and I'm going to put weightlessness down here because I have a picture I'm going to draw and talk about the difference between free fall and weightlessness. So, weightlessness is a sensation produced when an object and its surroundings are in free fall. Okay, so the surroundings part is important. All right, now let me give you a scenario. Let's say that you are in an elevator. Okay, there's a little cable holding the elevator up. I'm going to draw this twice because there are going to be two different scenarios. And let's say that somebody cuts the cable to this elevator. Okay, so here it is over here. The cable has been cut. When you would fall, you would come off the elevator, the bottom of the elevator a little bit, and then you would fall down at the same rate as the elevator is falling. But you wouldn't necessarily be touching the bottom of the elevator. Now, when this happens, you are in what's called free fall, where you only have the force of gravity acting on you. You don't have any normal force. Your air resistance is pretty much negligible because free fall happens very quickly. You don't have a whole lot of air resistance because you haven't gained up enough speed yet. So it's just gravity acting on you. That is in free fall. Now, the sensation that you will experience is called weightlessness. Now, weightlessness is not true. That is not a real thing. It doesn't exist. It's a sensation only. It is not a force. It is not a physics, vocabulary. It is a vocabulary term, but it's not a physics phenomenon. It is a sensation only. You can only feel weightlessness. You can feel weightless. Everything has mass. Any object that has matter has mass. Okay, so you can't ever be not weightless. So it's a sensation only. But the reason why you feel weightless is because your surroundings are falling with you at the same rate. So it feels like you have no weight. But it's not, it doesn't exist, weightlessness is not a real thing. Oh, let me erase this real quick. See if I have any other notes. I do not. Okay. So that's free fall and weightlessness. And so a good example of when you might experience this in real life, hopefully you are not, plummeting to your death in an elevator, knock on wood that never happens to you. I sure hope not. I wouldn't want that to happen. Anyway, the way that you would experience this safely would be on a roller coaster. So if you've ever been to Six Flags, you may have ridden on the ride called the Superman. So what it is, so if you've never experienced it, if you've never seen it, go look it up on YouTube. It's really interesting. I don't do roller coasters because I don't like the whole stomach in my throat feeling. That's not for me. No, thank you. So, but what you would do, the Superman, is you go up this really, really tall tower, they strap you in these seats, and then all of a sudden they just drop all of a sudden. And because your surroundings, your seat that you're in is technically your surroundings at that point, because you're falling in the seat, your surroundings, your seat, are falling at the same rate, you feel weightless, but you're actually in what's called free fall because you only have the effect of gravity acting on you. So that would be the Superman roller coaster. All right, let's move on to Newton's third law of motion. All right, Newton's third law of motion. So it says when one object exerts a force on a second object, the second object exerts an equal but opposite force on the first. Okay, so a great example of, well, let's do a couple of notes real quick. I'm going to write these in different colors, do a couple of notes for Newton's third law. This is called the law of momentum. So Newton's first law is called the law of inertia. Newton's second law is called the law of acceleration, F equals ma. And then Newton's third law is called the law of momentum. So these are also called action-reaction pairs. Newton's third law, it's a great example of action-reaction pairs. One example that I like to use would be dribbling in basketball. So the basics of Newton's third law of motion is equal but opposite force. Okay, so when you dribble a basketball, you are forcing the ball onto the ground, and so the ball actually exerts a force on the ground. Now, what you don't realize is Newton's third law of motion is real. It's really happening. So that means that the ground is actually exerting the same force back up onto the ball. And because of how the ball is manufactured, the material it's made out of, the ball will bounce back up at you. Now, if you did it with a different kind of, like if you try to bounce a bowling ball, that's a little bit different. You can get a bowling ball to bounce. It can happen. But because of the material that the bowling ball is made out of, it doesn't bounce as high as a basketball does because of the material it's made out of, also because of its weight. Anyway, a great example of this is Newton's cradle. And I'm going to go find a picture of this. Y'all bear with me. So here is a great example of Newton's cradle. So let's see if I can steal this, the one that's moving. Nope, it's not moving. Okay. Anyway, good enough. I'll be able to explain what I'm trying to talk about here from this picture. All right. What happens if you've never seen a Newton's cradle before? I'll go back to this. You can see this moving here. What happens is this one, let's look at this one on the left side over here that's moving. You pull the left one out, let's say 2 or 3 inches, and the momentum passes through the other ones that are not moving in the middle, and the momentum is transferred and it comes out on the other side. Okay, so let's look at this picture here. Okay, you would take this one here, you would pull it out, and it would be over here, so let's say that's 3 inches or something like that. And you would release it, and it would come in, and the momentum would pass from this one to this one to this one to this one. And then when it hits this one, there's nothing stopping it, so it swings out over here. Now, the law of conservation of momentum states that momentum is conserved throughout a system. Now, that's in a perfect world. That's without air resistance, that is without friction, that's without any of those things, and loss of energy. So, according to the law of conservation of momentum, well, we'll actually get into that in just a minute, then the 3 inches that it comes over on this side that you pulled it out on should also be 3 inches on this side. But that's not always the case. That doesn't always do that, okay? It's actually, when it comes back around, it's going to be more like 2.5 or something like that. Now, I don't know that for sure what it would actually be. We would have to take into account the mass of the object and what the speed was when it hit the others. And so we could actually calculate that, and we could figure out how much it would come off over here on this other side. We could calculate that, but that's some AP physics level stuff. We're not going to do that. Now, so let's talk about let's see. Let's go ahead and move on to momentum, since we mentioned momentum. This is black. Okay. So momentum is the quantity of motion. All right. Now, momentum, here I'm going to give you the formula for this. This is the Greek letter called rho. It looks like a weird sideways P, but it's the Greek letter rho. And so the formula is mass times velocity. Now, we have dealt with mass and acceleration. Oh, excuse me. We've dealt with that before. This is the first time that we're really seeing velocity. So momentum is dependent upon these two things, okay? If you have more mass, you will have a smaller velocity if you're wanting the same momentum. Okay, if you have a bigger mass, you have a smaller velocity to get the same momentum. If you have a smaller mass, you'll need more velocity to get the same momentum. Okay, they are directly proportional to each other. If one of them goes up, the other one goes down. If one goes up, the other goes down. Okay, so now mass is in kilograms, velocity is in meters per second. When you put these together, you get the unit for momentum is a kilogram meter per second. Now this one doesn't have a fancy name like Newton's for forces, but this is just kilogram meters per second. Okay. Let's move on to law of conservation of momentum. Okay, the total momentum in a group of objects doesn't change unless an outside force acts on an object. Now, so basically what we're saying is the momentum before will always equal the momentum after. You know, this is when a system goes through a change. You know, you change the mass or you change the velocity or something else hit it, okay? What it's saying is the momentum before this change happens should always equal the same as after this situation happens, after the change has happened. Now, it says unless an outside force acts on the object. So let's go back to Newton's cradle. Let me go back here. So let's go back to Newton's cradle. Technically, according to the law of conservation of momentum, this action with Newton's cradle should happen for all of eternity. Okay, now, this particular image is not correct because it is going on for all of eternity. If you did this in real life, it would not do this. Okay, it actually will slow down over time and eventually come to a stop. Now, the reason why it does that is because an outside force is acting on the object. Now, it's not that you're coming up and bumping it or something like that. The outside force that's acting on Newton's cradle is actually, there's an energy being lost through friction and being lost through air resistance. So over time, that takes its toll and it will eventually come to a complete stop. Now, there's actually a video that I would like to show you before we talk about collisions anymore. And so there is the physics professor, and I actually found this video several years ago, and I wanted to do the same thing in my classroom, but it requires me to attach a bowling ball to the ceiling from a string, and I didn't know how to do that without like bringing in maintenance people, so I ended up not doing it, but it would have been really cool. Excuse me. But one of the demonstrations because I would use the bowling ball on this, string all year long, but one of the demonstrations that I would do with it was to demonstrate the law of conservation of momentum. Now, this professor is a good actor, okay? And so he talks about how he's scared and things like that. He sets it up great to kind of keep his students involved. But he 100% knows what he's doing, okay? Now, the way he kind of explains what you're going to see is a little bit different than I've been explaining the law of conservation of momentum. He talks about it in terms of energy change. I'm talking about it in terms of forces. So he's not wrong and I'm not wrong. It's just looking at the same situation from two different perspectives. He's right and I'm also right, but it's just in two different ways. Now, when we get to types of energy changes, then we will talk about it in that instant in terms of energy. Okay, that's a couple of units from now. We will talk about the same situation, but in terms of energy. Okay.
I am such a strong believer of the conservation of mechanical energy that I am willing to put my life on the line. If I release that bob from a certain height, then that bob can never come back to a point where the height is any larger. If I release it from this height and it swings, then when it reaches here, it could not be higher. There is a conversion from gravitational potential energy to kinetic energy back to gravitational potential energy, and it will come to a stop here. And when it swings back, it should not be able to reach any higher, provided that I do not give this object an initial speed when I stand here. I trust the conservation of mechanical energy for 100%. I may not trust myself. I'm going to release this object, and I hope I will be able to do it at 0 speed, so that when it comes back, it may touch my chin, but it may not crush my chin. I want you to be extremely quiet, because this is no joke. If I don't succeed in giving it 0 speed, then this will be my last lecture. I will close my eyes. I don't want to see this. So please be very quiet. I almost didn't sleep all night. 3, 2, 1, 0. Physics works, and I'm still alive.
Okay, so I like this video because what he talks about is that when he released I don't know if it's a bowling ball, this large object, he had to release it at 0 speed. So if we're just dropping an object and not launching it, like I didn't push it when I dropped it, then the law of conservation of momentum, it's still it's still happening. Of course, it always works. But what I mean is you're still going to be able to trust the law of conservation of momentum because you don't have an outside force acting on it. If you put an outside force, meaning that you pushed the bowling ball before you let it go, then the law of conservation of momentum still stands true, and it would have come back and hit that guy in the face and crushed his chin. But because he launched it at 0 speed and didn't put an outside force on it, then that means that when it came back, it was just shy of where it started at, because he started almost touching his chin, and when it came back, it was a little bit lower, because some of it got lost in the energy transfer with friction and air resistance. So he trusted that 100%. So the last thing that I want to talk about are types of collisions. Now, this one is fairly important because this is essentially what your egg drop is based off of. So let's talk about egg drop for just a minute. When you drop the egg, the momentum of that egg is so large that when it hits the ground, the shell of the egg can't handle it anymore. So the momentum is stronger than the shell of the egg. So what you have to do in the egg drop is design some kind of contraption that reduces the momentum of the egg. So that's your goal. Okay, so let's talk about types of collision so you can use this to your advantage. Oh, got a little too excited there. Types of collisions. Okay. So the first type is called elastic collisions. Okay, this is where kinetic energy is conserved. Okay, and so these are when a very large object could be small. Let's just say we have a large object and a small object. So I've got a diesel truck versus one of those little half smart cars. And so let's say that this has a momentum of 30,000 and this has a momentum of 0 because it's not moving. In elastic collision, kinetic energy is conserved. So what this is saying is when this diesel hits the car, then kinetic energy is conserved and some of the kinetic energy passes to the car, and then this car will then move after it's hit. Okay, some of the kinetic energy is, so all kinetic energy is conserved, but it may be that some of it is passed on to the car. Now let's try this in a different situation. Let's talk about inelastic collisions. All right, so this is when kinetic energy is not conserved. All right, so same scenario. The only difference now is that it will not be conserved. So you've still got the same situation. Momentum here is 0. Momentum here is 30,000. And then when this 18-wheeler hits this little car, it's not necessarily conserved. And so some of it's going to be lost in the collision itself. So yeah, this car may move, but it may be just a little bit. It wouldn't move like it did a lot on this other one because you have kinetic energy that's conserved here and it passes from the 18-wheeler. Some of it passes from the 18-wheeler to the car, but here it would just be kind of a smaller one. So kinetic energy is not conserved for whatever reason. Now this may be because of the material that's actually colliding may have taken up some of that momentum, so it may have been lost like that. Because I'm just drawing this picture to give you a good scenario. Now, what causes the kinetic energy to not be conserved could be various reasons, okay? But I just need you to know the difference between elastic and inelastic. Now, the third type, I don't talk about this very much, and it's not even in your notes, is called a completely inelastic collision. Okay, and so kinetic energy, again, is not conserved. But this is when two things collide, like our 18-wheeler, here. Bring this up here. And our little smart car. That they will actually collide, and after they collide, they will stick together in one entity and then move together. So this may be because, like if you do it with a train car, when they on the yard, they actually, instead of like driving a train car to another train car, they will just bump it across the yard, and so they'll just hit it one hard on one side. The car hit it real hard on one side, and they'll bump it across the yard. And so when it finally hits the other car on the other side of the yard, they lock together and then move together. So that would be a situation where that happens.